enmarcada en la celebración de los 75 años del inicio de nuestro programa de Ingeniería Química en la Universidad Nacional de Colombia, sede Bogotá. Y este evento central lo hemos titulado Más allá de la Ingeniería Química, oportunidades y perspectivas para el país. Queremos iniciar en esta ocasión, en primer lugar, haciendo un agradecimiento a los patrocinadores que han hecho posible realizar este evento. Tenemos en primer lugar la Vicerrectoría de Investigación, la Dirección Académica de la sede de Bogotá, la Facultad de Ingeniería y la Dirección de Bienestar de la Facultad, el Grupo 200x200, AICUL, a las empresas Integral de Soluciones Tecnológicas IST, Industrias Químicas PIC, Ecosavia, Arintia, Cementos Alión, Cervecería 420, Cervecería La Herencia, Norlab, Alma Café, Cafeco Central, Natural Brand Coffee, Cervecería Tres Cordilleras, Cervecería Patriota y a la Asociación Cultural Hilos Mágicos. A todos ellos, muchísimas gracias. Y queremos agradecer a su vez la participación y acompañamiento del profesor Rafiqul Gani, de PSE for Speed, a su vez al profesor, a Felipe García Cardona, del Instituto Humboldt, y al profesor Arturo Jiménez Gutiérrez, del Instituto Tecnológico de Celaya, así como al profesor Néstor Yesid Rojas Roa, quien será nuestro moderador en la sesión de hoy. Entonces, vamos a iniciar en primer lugar haciendo la presentación de la hoja de vida del profesor Rafiqul Gani. En cuanto al orden del día, en primer lugar tendremos la presentación del profesor, luego la presentación de Felipe García Cardona, posteriormente haremos un breve receso de unos 15 minutos, luego de ello tendremos la presentación de Arturo Jiménez Gutiérrez, posteriormente haremos a continuación el panel entre los invitados, moderado por el profesor Néstor Yesid Rojas Roa, y posterior a ello ya haremos el cierre del evento por el día de hoy. El profesor Rafiqul Gani es director ejecutivo de PSE for Speed, una empresa que cofundó en 2018. También es profesor visitante distinguido en la Universidad de Ciencia y Tecnología de Hong Kong, en Guangzhou. A partir de 1985, el profesor Gani trabajó en el Departamento de Ingeniería Química y Bioquímica de la Universidad Técnica de Dinamarca, donde fundó el Centro de Investigación y Consorcio Industrial CAPEC. El profesor Gani se desempeñó como editor en jefe de la revista Computers and Chemical Engineering de 2009 a 2015 y actualmente se desempeña como editor de la revista Sustainable Production and Construction y es miembro de los consejos asesores de varias revistas internacionales revisadas por pares. El profesor Gani ha recibido 4 títulos de doctor honoris causa, fue presidente de la Federación Europea de Ingeniería Química de 2015 a 2018, miembro de la Academia Danesa de Ciencias, miembro del Instituto Americano de Ingenieros Químicos, AIQE, y miembro de la Institución de Ingenieros Químicos, INCHEM. Ha recibido numerosos premios, incluido el premio AIQE Computers in Chemical Engineering en 2015, la medalla de la Federación Europea de Ingeniería Química, Jacques Villermoz, en 2019, la medalla de la Institución de Ingenieros Químicos, Sargent, en 2021, y el premio de la Sociedad Estadounidense para la Educación en Ingeniería a la Excelencia en la Educación en Ingeniería Química en 2022. Ha publicado más de 550 artículos en revistas y memorias de eventos internacionales revisadas por pares, además de 5 libros editados y un libro de texto. Sus publicaciones le han otorgado un índice H de 75 en Google Scholar, 64 en Scopus y 58 en Web of Science. La investigación actual del profesor Gani incluye el desarrollo y la aplicación de métodos asistidos por computadora y herramientas asociadas para el modelado, estimación de propiedades, síntesis, diseño e intensificación de procesos y productos, e integración de procesos, herramientas con énfasis en energía, sostenibilidad, descarbonización y aplicación de enfoque de sistemas. Profesor Gani, it's an honor to have you here. Please come here with us. Les pido un aplauso para el profesor Gani. Muchas gracias.
See that here?
You want to- No, it isn't changing.
The helper who was here. The person who was here helping us. Okay. So thank you very much for the kind introduction. Thank you very much for also the invitation to come here. And I should give you congratulations for your 75th anniversary. It's a pleasure for me to give this lecture. I'm going to talk about sustainable process design, efficient, reliable, and very rapid. So let me start with what I say, a good information about what we do in chemical engineering, but also for us as humans on Earth. What I would say is that we human on Earth, we are the master of planet Earth. And what should we do to remain at the top? We need to tackle the challenges of resources that we have on Earth, like energy, like water, like food, and the impact we do related to safety, health, environment. And we can address these challenges by trying to find what we call a sustainable solution. I will discuss this in more detail. So this is my motivation to do this work. Let us look at why we call ourselves the master of planet Earth. What we can see is that all the kind of products that we need to be sustainable on Earth, we make these products. We have found a way to make these products. And because of that, what I would say is that that is a very positive contribution of chemical engineering to modern society. But should we just wait and see that these are all the things we need and we should be satisfied? Or should we try to remain at the top by finding new and better products? So that is what I would call that we on Earth have a lot of resources, which you can see in the on the slide now, but these resources are not uniformly distributed. So we have to use these resources to make the products that we need, but not just make the products, we need to find new and better products so we can be at the top and we can be sustainable. So the challenge then is what to make, why to make, how to keep it safe, environmental impacts, and so on. So this is one of the challenges which we hope we can tackle through sustainable process design methods. This is not a simple problem, it's quite a complex problem, and we need to find sustainable solutions. But whatever we decide in terms of what to make, how to make, when to make, they are all related to the effects on energy, to the effects on water, to the effects on food and environment and health. And also, if we take into account that by 2050, we on Earth will have between 10 to 11 billion people. And because of that increase in the number of population, the general GDP will need to increase. That will mean that we will have to produce more products that we need on a daily life. And because of that, we will need more energy, we will need more electricity, we will have more demand for water, and all these activities will increase the greenhouse gas emissions. So that's a complex, challenging problem. And the question is how to address the interactions of energy, water, environment, health, food, for this growing population, because the population is going to increase. What this lecture is all about is what can we do to address those challenges. And let's review first how we are getting all the products we need to stay on top. We find out which resources we will use, and we will convert them to products. But in order to do this, we need to use energy, we need to use water, we need to use all kinds of resources. And as a consequence of this, we impact the environment, the global warming potential increases, ozone depletion increases, toxicity level increases, and many more. And at the same time, we produce a lot of waste. So if we think of that, all the processes that give us the products we need, from the raw material, the U-tube that you see could be representing all the processes on Earth. And then all the resources we put into the U-tube, and we get only 25% of useful products or useful services. And that is not sustainable. It's too much waste. And according to most experts, and this last number was given in 2007, it has not changed very much. We need to improve our processes by order of magnitude, not small improvements step by step, but order of magnitude improvement. So for sustainability, significant and rapid improvements are needed. And now I will briefly also explain what we mean by sustainability and sustainable development. On the y-axis, you can see that. On the y-axis, you will see a green curve going up. That is representing the human development or human progress on Earth. And at different times, you can see some curves going up and going down. Those curves are showing different technologies that before they became redundant, we found another technology to take over, so the green curve can always go up. And as long as this goes up and we can replace any redundant technology with some new technology, we on Earth can. So from that point of view, sustainability means the ability to sustain or the capacity to endure changes. And sustainable development means development that meets the needs and aspirations of the present without compromising the ability of future generations to meet their needs. And this is a very important point. We have to question ourselves, are we doing what we are doing now without thinking of what will happen to the next generation? One could question that many of the things we are doing now, it is going to affect more negatively the future generation. But that is not what sustainable development was supposed to mean. And then one question is, which is the redundant technology that we are going to get rid of and a new technology that is going to come? Would it be a new way of communication through the smartphones that we have, maybe even smarter phones, or communication or travel? What would be the next technologies that before they became redundant, we found the new ones? So that hasn't been decided yet, but we have to see what will happen. Now, with this background, I want to introduce a new definition of process design. What you see on the screen is the normal, conventional definition. We take raw materials, we take utilities like energy, water, and others. We make our product through a process, and we create a lot of waste. And we also impact the environment. That cannot be a good definition. We need to improve this definition. So we say that it has to be sustainable. That means it has to be economically feasible. It has to reduce the waste. It has to be utility efficient, meaning electricity, energy, water, They have to be more efficient in terms of usage. It has to be environmentally acceptable. It has to be safer. It has to be operable, and many more. All these things need to be included in the design of the chemical process. So then what we can say is that in addition to satisfying all those criteria, we also, the design that we make, it has to establish a sustainable production, which means that how long in the future the process can work to give us the product, adjust to changing markets, survive global competition, tackle demands for innovative products, and many more. So sustainable process design in this case then means synthesis of the process, design of the process, and innovation of the process. And very briefly, what do we mean by synthesis? We mean by synthesis is that if we have raw materials and we want to convert to process, how many processing steps will be needed and what kind of process operations would be needed. What you see on the left is a list of process operations. So how do we configure them and in which sequence they will be needed? So that would be a process synthesis problem. There are different alternatives shown in the picture, and what we want is the ones marked in red. So that would be, for example, optimal processing path or a flow sheet that will convert a selected raw material into a desired product. But that's not enough, because that is just the process flow sheet. We need to know more details of that process flow sheet. We need to know what is happening in each of the boxes on the processing step. And that is the design. If that box is a reactor, we need to design the reactor. If that box is a separator, we need to design the separator, and so on. And the reason we need to do all this design is that so that we can calculate how much energy it uses, how much waste it makes, and based on this, we want to calculate the economics and the environmental impacts and so on. So that will be the design, but do we stop there and say that's enough? And that is where we come now, because that is not enough. We have to prove that it is the best. And so we need to find more innovative solutions compared to what we have now. So we take the design that we have, we look at different ways of energy demand, supplying of the energy demand, and we find out if it is energy that we would like to improve, how to do that. It could be also environmental impact. It can also be effect on the human health. All of these things we will need to look at, and we will need to improve. And what we would like to achieve is this, something like an ideal, totally renewable system. So in order to achieve this one, we have developed what we call a multi-stage hierarchical solution approach. So the first stage, as we have shown before, is the synthesis stage, where we find the flow sheet, then the design stage, where we design, and then the innovation stage, where we improve. The issues are, for any problem, where is the system boundary? If you're developing or building a plant in Bogota, should you think only of the environment in Bogota, or also the surrounding areas, or also all of Colombia? So all of these things need to be looked at. So the system boundary is very important. Then models and data are very important. How much knowledge do we put in order to solve this problem? And also data comes from different sources. How do we make sure that all the data are consistent? This gives rise to a multi-objective, multidisciplinary problem, and we need to tackle that. And from a chemical engineering point of view, chemical engineers are good in gluing all the different things together and solving multi-objective, multidisciplinary problems. So we can think of, we are the glue that puts everything together in a very smart way. So what we are doing then is, at least in our method, we have all the prior information, knowledge that we learn in the bachelor, master's, PhD. We need to use all this information in the solution of the problem. In addition to that, we use computers in order to speed up the solution. Because what we can do by hand in 1 hour, the computer can do probably in 1 second. So if we can use the computer to do all the things that we can do ourselves but takes a long time, then we will speed up the time. And then you have, I'm sure, heard of artificial intelligence. We should not use it just blindly. We should use it so that the complex problem that we have can be simplified. And then we are using a lot of models and data. Again, to solve this complex problem, we can use techniques like machine learning. So we selectively use these techniques together with our a priori knowledge to find the best solution. So now we come to how do we use new and useful concepts. The new useful concepts can be, as I mentioned, artificial intelligence, machine learning, cloud computing, and many more. Our models, our solution methods, computer-aided tools need to use these techniques. We want to solve problems correctly, consistently, and very rapidly. And then the question is, how long should the solution of sustainable process design problems take? I didn't put 1 minute. We could also put 1 minute. Should it take 1 minute, 1 hour, 1 day, 1 week, 1 month, 1 year, or more? And we would like to solve it very, very fast. We don't want to wait for 1 year or not even 1 month. And then the basis of all that we are doing, I will show it through a multi-layered view of chemical engineering. As we said, our core work in chemical engineering is what you see at the center, is to convert raw material to products we need, and we need a process for that. So from left to right, you can see resources are coming in, and we are converting them to products that we need. But we need a process. And the process is where we use our intelligence, what we have learned. We use modeling, synthesis, design, control, numerical methods. By these, we design the process, we operate the process, we analyze the process, we develop the models. That's the core activity. And then you can say, is that enough? It's obviously not enough, because we have to augment our knowledge, the design methods that we know, the thermodynamics that we know, the fundamental concepts that we know. We need to augment that by combining science and engineering. And that's where AI, machine learning, model predictive control, process intensification, all of this come in. And the result of all of this is that we get a sustainable, efficient, and reliable technologies. So from bottom to top is what we get by applying our experience, what we have learned. And from left to right, now before we were only saying that we will use the resources, now we are saying what is the demand for the resources, what is the availability of the resources. The resource that is available in Colombia may not be available in Denmark, so we cannot produce the same thing in all the places. So we need to take that into account, and then we need to have improved. Remember that we need new and better processes than before, or products than before, and we need to make less waste. So by adding an additional layer, we can tackle all these issues. And then we can ask, is that enough? And I would say no, there is one more layer needed, because we have to think of why are we becoming chemical engineers. We have a duty to perform to the society. So our final product is towards, we can call circular economy, sustainable development of society. Remember that we humans need to be at the top on this planet Earth. So that will ensure that we are there. And then to do that, we need to use different ideas, different disciplines, data sources. We need to integrate all of that. And then as far as the resources is concerned, we now not only look at demand and availability, we also look at location, recovery, recycle, all of this. All of this then gives us the perfect product and the process that we need. And then we can see that the core is the fundamental layer of process systems engineering. This is every chemical engineer needs to know that, should be able to convert raw material to product and design a process. That's a must for every chemical engineer. Then if they have that, they can take additional master's degree, PhD, all this to improve on that fundamental design. And then based on the experience in the fundamental and middle, they can serve the society. So that is the multi-layered view of chemical engineering that is very important to satisfy our sustainable process design approach. And what is important here is that in all these steps, modeling is very important. And so I will spend a little bit more time on modeling. Why do we need models? On the right-hand side, you see the problems that we would like to solve. It can be related to design, production, planning, safety, many more. And on the left, you can see the system for which we want to solve this problem. It can be process or product. It can be operation. It can be environment. It can even be business. We want to solve these problems. If we knew enough about the system, we should be able to solve the problem. But unfortunately, we do not know enough, and we do not have enough data also. So in order to know enough and to have the missing data, we develop models of the system. And then by solving the model equations, we generate additional data that helps us to solve the problem. So once we have the model, we can develop model-based systems, and then we need numerical solvers like ML and others that will help us to solve the problem. And then we need algorithms, methods that will use the models to do the design. That's where AI can come in. So all of these are needed, and the modeling is at the core. Examples of model-based systems are model-based systems for process synthesis, process simulator, control monitoring system, planning scheduling system, and many more. The objective of the models and modeling, remember, should not be just to replace experiments. That doesn't help us to get the innovative solutions. We need innovative predictive models. And since I said that one of the model-based systems is a process simulator, that's again one of the most important model-based systems that we have developed. At any time on Earth, somebody somewhere is using a process simulator. So that's very good. That's our, let's say, what we have developed for the society. But is that enough? We have the process simulator. Can we solve all problems that we have, or the complex problems that we have? Sometimes when I talk about this, and some people, mostly from industry, would say, but we have Aspen or we have Pro2. So the question would be then, can Aspen or Pro2 solve the problems that I'm talking about? So let's say that if we did not have the process flow sheet, can the simulator give us the process flow sheet? Or if we didn't have the model that we need and we couldn't find it in the process simulator, can it give us that model? Or if we needed to design an innovative new operation, will the process simulator be able to handle it? Or If we wanted to use a new catalyst or a new solvent, how do we introduce those? So what we see is that these tools are not in the process simulator, but to solve the sustainable process design, we need them. So what I would say is that we can still solve these problems, but as a trial and error method. And what do we do then in a trial and error method? If we didn't have a flow sheet, we give our assumption of a flow sheet, we solve all the problems. If it does not satisfy our requirement, we try again. So it's a trial and error method. By accident, we can get a good solution, or we can try and try and try, and we never get the solution. Or if we even get a solution, we cannot be sure that that is the best solution. So if you remember that we had the objective that we have to improve by order of magnitude our process, trial and error is not going to give that unless we are lucky or we by accident we get it. And for our sustainability, we should not depend on luck or accidental solutions. We have to be able to find them. So how does a process simulator perform all the extra activities? By trial and error. We want to avoid the trial and error. So our proposal for an integrated system where we put all the additional tools that are needed is shown here. At the top, it's a complicated diagram, but I'll just show you the main features of it. So on the left-hand corner is the library of databases. We need a lot of data, so we have to have not just one database, we have a library of databases of different kinds. Then we want to do some fast calculations. We don't want to depend on whether the process simulator has all the models, has all the data, can solve these problems. So we can develop new, faster models that can give us the data that we need without doing the detailed process simulation. If we do not have a process flow sheet, or we do not know which catalyst to use, or we do not know which solvent to use, we can develop methods that will very quickly tell us these are the material that should be used. And then once we have all of this information, we can actually use a process simulator. And then after that, we need to analyze with respect to sustainability, with respect to economics, with respect to life cycle assessment, all of that, and find out whether that process can be improved further or not. So in all of these activities, we see that process simulator is just one activity, one step. So that's why if we just base on process simulator, it's not going to solve our problem. We need all these other tools and methods all integrated together so that we can solve the problem. And if we can do that, we can solve the problems very, very fast. So then, as we said, that we have a three-stage method: synthesis, design, analysis. That is decomposed into 12 tasks. I'm not sure if you can read it, but the first three tasks are related to process synthesis. Then tasks 4, 5, 6, 7 are related to rigorous simulation, but step by step, not directly going to rigorous simulation. Then 8, 9 is analysis, trying to find out the economics, the sustainability, and find out where the weak points of the process are. And then finally, 10, 11, 12 are steps to find innovative new candidates. And there, the approach is define targets for improvement and match these targets through alternatives. And by definition, if we can find an alternative, then by definition, it will be more sustainable. And then what you see is the whole set of tools, and it follows the multi-layered view. At the core, we have the main interface that guides the user through the different steps. Then the first circle after the core are the main calculations. And for each of those main calculations, we need a lot of different tools, and that are in the outer circle. So that's how the structure is, and it is made in such a way that all the problems can be solved consistently, correctly, and very fast. Now we can also see that all these products that we are using every day, even all the bottle for the water and many other, these are all chemical based products coming out of chemical processes. And how did we design them? 30 years ago or 40 years ago, did they have all these tools? They did not, but they did by experiment. And these are still being done by experiment. I would say more than 90% of the product and process are designed by experiment. And that is fine, because the solution we get, that solution is verified by experiment. The only problem is we do not know if it is the best. We know that a solution is there, it works. And maybe it took a long time, and maybe it was costly. So, but we get a product or a process that works because it's verified. Now, and that is what I will call reality. What happens if we replace the reality with virtual reality? You have heard of the terms these days with computer-aided things and digitalization and so on. That's the virtual reality. But will virtual reality give us what would be the advantage? Let's say, if virtual reality uses the same data from the reality and makes a model and then finds the solution, then by virtual reality, at best, we can find the same solution we could have found by experiment. That's one thing. The other one, and that's the improvement, the experiment may take time, may need money, cost. The virtual reality would be faster. So virtual reality is, compared to the reality, is faster and less expensive, but it does not give us the better solution, because we have just used the same data to represent our system with models. What we need are predictive models that can go outside the data set. If we can do that, then virtual reality would be good. But otherwise, it's just saving us money and time, not the most important part, which is to get new and better products. For that, we need to have predictive models. And that can be done also through integration between reality and virtual reality. We help the reality, that is experiments, by telling them under what conditions the experiment should be done so that useful data can be obtained. And then the data can be used in virtual reality to get models that would be predictive, outside the box. And that's what we need. And so now, with that as the background, what we see is that whenever we want to solve sustainable process design problems, we need to make a lot of decisions. And one of those, many of those decisions are related to defining the correct problem to solve. And it can make a big effect. And as the cartoon says, why is 1.5 degrees, increasing 1.5 degrees so important? The difference between 1.5 degrees is whether we have ice or whether we have water. So think of if all the ice melted because of 1.5 degree increase, what will happen to us? So that's very important. Also, we should not get wrong conclusions based on what we see. So yes, we can see many things. AI can help, but we need to be careful. So now the kind of problems we can solve, like we can improve the process. Process intensification has been said that it can improve the process. So, but process intensification can mean many things to many people. And let's define. Process intensification can mean higher productivity, uh, species utilization, multitasking, increased efficiency, safe and reliable operation, economic improvement, many more. Which of those criteria are we going to satisfy? We have to decide that. And then if we decide that, what would be the means by which we should achieve it? Should we find a better reaction? Should we do better species allocation, better management of heat and power, reduce size or increase size, define different equipments, and many more? So these would be the means to achieve. And then there are methods by which we can achieve. So we need to identify what we want to improve, how we want to improve, and then we can use the method to improve it. And the same goes for decarbonization. It can mean different things to different people. So let's say at least three of those measures we can say. Decarbonization would be CO2 released versus resources used, temperature increase. It can also mean effects of climate, availability of resources, uses and needs of products. It can also mean or connected to the 17 Sustainable Development Goals set by the United Nations. How do we achieve these? We have to reduce CO2 emission by reducing energy demand or utilize captured CO2, so generate only the amount of CO2 that can be captured and utilized, look for integrated solutions, and many more. And then there are different means to do that. So again, if we say we want to do decarbonization and we want a sustainable process design, we need to define the problem correctly. And here, at least we can be grateful for some of the institutes that are studying these things, because they have studied from now until 2050, if we want to satisfy the requirement of 1.5 degrees increase in temperature and no less, how much CO2 needs to be captured. And out of that, how much should be from the industry. So now we have a very well-defined target. Can we find all the chemical industries and others that are releasing the CO2? Can we capture them or redesign so that this CO2 will not go? If we can make sure that this amount of CO2 does not go out, we are sure that we can satisfy the 1.5 degrees increase in temperature. And the last one would be circular economy. It's a very hot topic, but what does circular economy mean and how is it connected to sustainability? Again, there are different measures of circular economy. How can we achieve it? What are the means to achieve it? And what kind of research is needed to achieve it? Then finally, I'm not going into details of this, but I will show you some examples later. The last point in here is how do we define the problem? If you look at this plot, on the y-axis is environmental impact, on the x-axis is economic profit. Should we go for profit? Don't worry about the environment? That's what we will get. Or should we worry about both? And that's what we will get. So we need to define the problem so we know which solution we are going to get. So next comes the scope and significance of the problems to be solved. Should we depend on a single source of energy, or should we look at multiple sources of energy and combine them? Also, what should be our solutions? in the short term or in the long term. So let us look at, and here is the boundary where it is important. Here is the chemical process. We put our resources and we get our product, and maybe we get waste and CO2. And we could redesign in such a way that CO2 would be zero. But would that be a solution we are looking for? Because the boundary is wrong. In order to operate the plant, we need energy from a power plant. So although we will not generate any CO2, the power plant will. The indirect CO2 in this case can be very large. So we need to see which are the energy demanding technologies, like a chemical process, like a car, airplane, they all require energy. And then which are the energy supplying processes, like a power plant. And then for that energy supplying process, which raw material should we use? Fossil fuel or solar or wind or nuclear? So we need to find a good combination of this so that we have a sustainable solution with net zero CO2. And here is an example of that, what could be done. We have the power plant, we have some other processes where CO2 come out. We capture this, we use this together with our raw materials in the process. And then we get our products. Whatever waste we have, we try to recycle. And then if we can find a solution like this, that would be the kind of solution we are looking for. Decarbonization would be a good example. And I will come back to this. So this is a real problem solved according to what I had shown. We captured the CO2 coming out from a power plant. We design a process, and then we want to go to zero CO2. So here is the part that captures the CO2. Then we use different alternatives to create the hydrogen, make the hydrogen. We use the hydrogen and CO2 to make different products. And we have used at least some of the CO2. But the question is, how much of the CO2 have we used? If we look at the results, they look very good. We have achieved for that within boundary a negative CO2, and we also have achieved profit. That is very fine, but the amount of CO2 that we have captured, only part of it has been used, because for the product, 1 CO2 gives 1 mole of methanol. So, but we capture much more CO2 than we can use methanol. So what we have is a lot of excess CO2 capture. And what do we do with that? And it turns out, at this moment, we can only sequestrate it. Otherwise, there's no other solution for it. Unless we can increase the demand for methanol, everybody uses methanol for everything, then it will be good. Otherwise, it's not possible. So even though this looked like a very good solution, unfortunately, most of the captured CO2 has to be sequestrated. And then process intensification tells us that if we have a chemical process, we can convert that process into a reactive distillation, or we can combine different distillations into a dividing wall column distillation, or we can combine distillation and membrane to have a hybrid membrane separation. So all of these things can be done. But in order to do these designs, it can take a lot of time, it can take a lot of effort to find out. And then do we find out afterwards that we have taken a chemical process, analyzed everything, designed the reactive distillation, and found out that it was not really good. It didn't satisfy our requirements. So all that time would be wasted. So what we have done is we have developed a simple method where we ask 7 questions. And if the answer to these 7 questions is yes, then that technology can be used. So here are the 7 questions for reactive distillation. For the original process, based on the original process, we can ask, in the original process, is the reaction exothermic? Is there only one reaction? Does the reaction and separation involve liquid and vapor, and so on? And if all the answers are yes, you can take that process and you will find a reactive distillation design that will save at least 20%. That's the minimum target for improvement. Similarly for a dividing wall column, similarly for a hybrid separation systems. And to answer these questions, we already have all the data for the process. And so I will show you, before I go to the examples, what are we doing with this kind of techniques. And this kind of curve, maybe you're familiar with because of the pandemic and the COVID. On the y-axis, you can put number of infections or number of people dying, and on the x-axis is time. If it is no action taken, we go up the gray curve, and it is above the horizontal line, and we have a lot of deaths and a lot of problems. If we can take some action and make the curve flatter and below the horizontal line, then we have solved the problem. So this is what we are trying to do. Whatever is the problem, we are trying to flatten the curve, and so we can solve that problem. And a measure of solving that problem are the 17 Sustainable Development Goals. So here is one where hybrid separation would be feasible. So we asked the 7 questions. If the answer is yes, then the 2 colored columns can be replaced with a hybrid column, and that will save a lot of energy. Now this is not a long-term solution, it's a short-term solution, because the process exists now, and just by making a small change, we can improve the process. How much improvement can we do? It is between 10 to 50%. And then the number is here some years ago. Now it is actually 400,000 distillation columns operating in the world. If we can save between 10 to 50% energy of all these 400,000 distillation columns, you can imagine how much saving of the energy and how much reduction of the CO2 we can achieve just with the short-term application. The dividing wall column, this is a chemical process, and we can make different combinations of combining the 2 distillation columns that are next to each other. And if we do that, we would be saving around 45% of the energy compared to the original process. And that again is a short-term solution. So I can skip the remaining. And now I will show you an example of reactive distillation. This is a process to make methylene chloride from hydrochloric acid and ethylene or some other compound, methanol. So actually, methanol and hydrochloric acid will give methylene chloride. This is the original process. There is a patent for it. You can find all the information. We asked the 7 questions, and the answer is yes for the 7 questions. The base design was using so much energy, and the purity was 96%. Because the 7 questions answer was yes, we could design a reactive distillation, and in addition to that, we needed a separator, and we saved. You can see how much energy we saved. Nearly 90% energy is saved, and the product purity is better. And we can also find another alternative with similar improvements. So we didn't have to do trial and error here. We had the original process. We asked the 7 questions. It was yes. We directly went to the solution of the reactive distillation. And then I talked about capturing the CO2 and utilizing it to make a process, but also integrating it with the energy source. That is how to get the power, how to get the water, everything. We can combine all of this together and we can design a profitable process and at the same time net zero CO2. And this is a process we have designed in China. The product is xylitol and it's a totally self-sufficient. They have sun, so we use the solar energy. They have a lake, we use the water from the lake, and everything is self-sufficient. It is not generating any CO2. It is giving profit to that location. Application of then decomposed method in synthesis design and innovation. And again, it's a process that it shows that it is much better than what is in the literature. And this process is making succinic acid. And you see in different columns, there are different boxes with different color. It means that these are already known technologies. So we take these known technologies, combine them together, and try to find one combination that is better than all the others that are found. And the different colors are different processes that already exist. And so we found this process that is better than any of the others. And then if we compare, and we also use process intensification, so the number of operations here, and if you compare this to this one, is much less. So that's an intensified solution. And totally innovative intensified solution, it does not exist. Compared to the base case, which is the boundary, we have alternatives that are much better. So that is an example of sustainable process design. We can do also for other processes like chemical process. I will go through this very fast. We combine hydrogen and methane and toluene to get benzene and biphenyl, and the process flow sheet is the one that you see at the bottom, obtained by synthesis stage, and then we design it, and then we generate all kinds of alternatives, and then the final optimal design is this one. We do the cost, we analyze the sustainability, everything, find out where improvements can be made, and then we generate the final improvement. So then you can see at the bottom the profit. Our first solution gave 933. Our last solution gave 1,527. So significant improvement is possible through synthesis design and innovation. One thing I did not discuss up to now is we are talking about chemicals, use of chemicals, products that have chemicals, and these chemicals can be dangerous. Some of them are very good, some of them are not so good, but some of them are very bad. And if we do not know about those chemicals that we are using, then we are driving a car blindfolded. So anytime we can have an accident. And the reason for that is up to now, we have data only about 40 to 60,000 chemicals, but we are using more than 1 million chemicals. So are we just waiting for the next disaster? What can we do about it? We have to be very careful of this. So we need to have a framework where as soon as we find the chemicals that are in the process of the product, we can identify them, we can substitute them, and then we can say this product or process is safe. All the dangerous activity of the chemical has been taken care of. And if we can do that, then we will have a much better solution. So what you see here is just some gases, and that are analyzed in terms of their hazard effect. And the gases include methane, hydrogen, carbon dioxide, refrigerants, phosgene. Now, which one would you think is the most dangerous of this? Carbon dioxide, phosgene, refrigerant, hydrogen, methane. It turns out that carbon dioxide is the least dangerous. Why are we spending so much effort to capture the carbon dioxide and make sure that the emission is zero? It's because of the volume of carbon dioxide that we release. If the same amount of methane was released, we will all be dead by now. So we have to be very careful of these gases that can come out and what to do. Similarly, we can take solvents, and I put this example because I received a paper to review, and the authors were saying this is the magic solvent, organic chemical. And I looked at how they found everything was fine, but then I said, well, let me check this chemical in my hazardous database, if it is hazardous or not. It was not only hazardous, it was listed as a banned chemical. So it's not enough to find a process where a chemical can be used. One has to find, is it acceptable or not, and what precaution one should take. So I will not go through this in detail now. The second last slide, I started with showing also the sustainability. Remember the green curve going up. So that's fine. As long as the green curve is going up, we are sustainable. But there is also another curve that people do not show, and that is the one which is the blue curve that is going down. And what is the blue curve? It is the resources that we are using. The more product we make, the more resource we use, and we deplete that resource. So what does it mean? From a capitalistic point of view or Western society point of view, we need to always grow the business and make a process sustainable. That process makes more profit, and the business owners would like to grow that business, make more cars, more TV, more product. Making more cars, more TV, more product would mean use more and more resources. And when the green and the blue curve intersect, we are at the point of unsustainability. So by making something more sustainable, we actually kill the process faster. So my question here would be, is the way we do business of growing our business, because we need to grow our business, otherwise venture capitalists would not give us the money, they need to see the growth. But by growing it, we are also killing it faster. So it seems like sustainability and capitalism probably does not work. So finally, what I would say is that we need to understand the problem and learn from our mistakes. We need to take action and use appropriate tools to take action, make wise decisions, or influence the decision makers, because sometimes it's the decision makers who make the wrong decisions. We need to help them to make the right decisions. Avoid trial and error solution. Define target, match target is a much better way to do these things. There is no trial and error there. Use methods and techniques consistently. Develop new tools if necessary. Evaluate benefits, both short-term and long-term. With that, I finish my lecture. Thank you for your attention. I would be happy to answer questions.
Thank you for your nice presentation. Do we have any questions?